available. So the group that is working at the auditorium can relocate to one of the classes here. So the people from the administration will give you a code to open the door, and that's it. About tomorrow, we'll have 5 presentations. I think Renato told you about, but I can tell again. So 20 minutes presentations, okay? And then you have 10 minutes for discussions. And it would be really nice if you, not only the professors and the monitors ask questions, but everybody can ask and comment and so on. That would be nice. Okay? So about presentations, well, I think everybody knows what a presentation is. I mean, it has to be some general context and the model, and what was also interesting here, the model and so on. What for is the model? I mean, what is the question that you are answering? What's the analysis? Why is the analysis important? What you obtain it gives you some insight about the system you are considering. Okay, so that's it. Okay, and now it's our last class today. It's divided into parts, connected one to the other. But so the first, I want to do some math and about vector-borne diseases, and then we will see largely informal discussion of what are some of the research topics at the frontiers of mathematical models in epidemiology. So vector-borne diseases, I will, instead of saying always a vector, the vector, and so on, I will call it a mosquito, okay? But obviously you can also think it's something else, although there are some things that are different. I won't comment more at the end. For instance, fleas they stay on your body, they live on you. It's different from a mosquito that bites. Okay? But okay, so think about mosquitoes. So, well, we will consider that mosquitoes can transmit a disease. This has been developed initially for malaria, but obviously other mosquito-borne diseases, this works in the same way. So what's the idea? You have, again, compartmental classes, susceptible, infected, and recovered humans, and susceptible and infected mosquitoes. Mosquitoes don't recover. They stay with the thing. Okay? Usually that's they don't have an immunological system that can do so. Mosquitoes don't recover. So therefore we will have susceptibles and infected mosquitoes. I put an index M for mosquitoes, and susceptible, infected, and recovered humans. Okay? I put an M here for consistency, although there is no need. So, and the infections occur due to the contact of an infection human with here, a mosquito gets infected because he had contact with an infected human, and vice versa. A human gets infected because it has contact with infected mosquito. Okay? So, okay. So, you can already, after this week, all your work and courses, you can already start imagining the equations here. That's probably not difficult for you anymore. But there's some particularities. Let's talk about them. So we will first consider the rate at which humans are bitten by a particular mosquito. Okay? So I will call this R. And I will say that this R is some biting rate divided by the total number of humans. What does it mean? This is the number of bites that a mosquito gives per unit time. Okay? We are considering that they are that is a constant. Obviously, we could have a distribution of biting things. And this is the total population of humans. So this means this is the quantity of bites that a single mosquito will bite per humans, okay, per unit time. Then obviously if you have a million humans, multiplied by a million humans, that will give you how many people have been bitten by the mosquitoes. Okay? So, with this, our model will look like, that's the kind of what people would call the standard model for vector-borne diseases. You have to write for the humans 3 equations. Plus 2 for the mosquitoes. Okay? 5 equations. 5 equations. Okay? So, first, let us put a, for instance, quite general situation. I have a certain birth rate for humans. Remember, we had done this when we discussed vital dynamics, okay? And then I will write that you have this rate, R, times the probability that an infectious mosquito effectively infects a human given a bite. But not all bites that are infectious, okay? So there's a probability, which I will call T(m), the probability that when a mosquito bites you, you actually get infected. And then times I, index mosquitoes, times S, index humans. Okay? So you have an encounter, infected mosquito, susceptible human. There's a probability that this encounter generates an actual infection, and this is the number of bites per unit time per humans. Okay? And well, then you have also some mortality. Okay? Yeah. It is already here. In general, not, but yeah, no, but usually you take the human population for certainly being constant. Okay. About the mosquito population depends. Are we talking typically, for instance, you could have if you think like dengue or even malaria, if you think I'm in a temperate climate, so that probably the number of mosquitoes is small and constant. And if you are like near the equator, where the conditions for the survival of the mosquitoes are always given, then the seasonal effect is not so strong, then it probably can also be constant. An intermediate case, subtropical case, then you have the seasons of the mosquitoes, and then the mosquito thing will be not not constant. But humans, yes. And this comes also from the fact that the turnover time of a population of mosquitoes is much, 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 much faster. I mean, the population will be replaced by new mosquitoes and so on at a rate of some weeks or months, while the population of humans has a lifespan of 50 years at least, and so on. So at the end, normally you will take this guy, all of these guys, to cancel this and have a constant population with vital dynamics. Yeah. So then you have here, all of these guys go here. And then there's also the death rate of humans which are infected minus the humans that go to the removed class. Yeah, well, is not minus mu human, and which eventually may also die. Okay? So it's the same steps that we have given by all other models. Okay, and only a little bit different form of writing here. The things is instead of a beta, I'm separating the R from the probability. Yeah, sure. You are right. Thank you. Yeah, it was right here also. And then the susceptible mosquitoes. Well, there's a birth rate for the mosquitoes. Okay. Then you have something which I will use index M ash, which will be the infected human infecting a susceptible mosquito. And then there's the death rate of mosquitoes. And here you have the mosquitoes entering this. And living. That's 5 equations. Okay. So, you are probably concerned that I want to do all the full analysis of the 5 equations now. And you don't have to be concerned because we won't do this. Okay? But what do we want? We want the same thing that we want most of the time. We want to know first R0. Okay? And then look at R0 and see if I have something interesting with the R0. Okay? So you could do next generation matrix or whatever you want, but I will make a calculation of much simpler, okay, using the fact that we have done this kind of calculations many times. Remember, but SIR model, it's R0 is just the beta over the gamma, okay? So that's the transmission rate divided by the duration of the infectious agent, okay? So therefore, we want now calculate R0 as given a primary infected mosquito how many secondary infected mosquitoes will arise, okay? So it's mosquito to mosquito. That's our definition of R0. I have one mosquito that obviously there is the human, but the human then may also infect new mosquitoes. How many new mosquitoes do you have given a primary mosquito? Okay, you could do this also in different ways. They could have kind of two kinds of R. The R0 for mosquito human, and then for human mosquito, and so on. But this is the simple way, and that's the usual thing. So given this mosquito, the number of infected humans will be what? So this has to be this guy, okay, which is what usually was the beta, okay, divided by the duration of the infection of the mosquito, not of the human, because it's the mosquito is transmitting, not the human to human. So this will be R T-M times mu hash times the total number of humans also, okay? So this is the number of secondary cases, which is actually equal to our B times divided times T-M divided by mu M. And now the number of infected mosquitoes by human. Okay? Each human will affect. So this has to be with this guy here. Right? So this will be R T MH by total number of mosquitoes divided by the time a mosquito, a human stays in the infected compartment, which is 1 over mu plus gamma. Okay, which happens to be B T M H divided by mu M plus gamma M plus the ratio times the ratio of N or M divided by N humans. B is the biting rate, the number of bites an infected mosquito, mosquito bites. So number of bites per unit time. Okay? We are considering a very simplified situation here also, okay? Because we are considering that the disease in the mosquito does not affect the biting rate. Okay? If you are working with a very specific disease, we are working with vector-borne in general, I don't say even the name of the mosquitoes, okay, with species and so on. But if you do something very specific, maybe if you have a biological background, you could modify models in such a way that you have a biting rate for the influenced by the fact that a mosquito is sick, infected. So now you have to multiply one. This is the number of infected mosquitoes that a human produces. But then I have all those humans that came from the first mosquito. So the R0 will be B squared. Okay, this times this, right? Time M hash. I made a mistake here. That's not the mosquitoes here, okay? That's the humans. because this is the time that the agent, which is the human, stays in the compartment of I. Okay, so it was, the index was wrong. Sorry. Then you have this mu index m times mu index h plus gamma h times the number of mosquitoes divided by the number of humans. So, R0. If you use the usual way of working that out in using dynamical system theory, next generation matrix, and so on, you would have obtained the square root of that, actually. Which is not so bad because this is a two-step. Okay, so the R0, define it as at what I defined here. This guy is this, but the condition for the instability of the disease-free equilibrium is not exactly this, it's the square root of that. But anyhow, the square root of 1 is 1, and therefore the bifurcation point is the same. Okay? So now, what's interesting about that? Well, first of all of these things here, you don't know. But you cannot do this in this. I mean, you would have to take a person and put it, I don't know, the arm for the mosquitoes and see the probability that they actually infect you. Okay, but this is it's not a lot. It's not possible. Although we know for malaria back in the 50s, there were some experiments like that made in Russia. Yeah. Yeah, they came from somewhere there. Yeah. Well, the biting rate is also, I mean, you cannot know exactly, but well, the biting rate, I mean, it will not be thousands per second, okay? So you have an order of magnitude of the biting rate. Yeah. So then these guys, you know, that's the mortality of humans, that's the 1 over gamma is the time duration of the disease, that you can know. That, the mortality of mosquitoes, not so nice. But I mean, you can, at least at populational level, more or less know how long a mosquito lives. Okay, so you have not a number, but you have a range of numbers. But actually, these guys, you don't know. It will always be fitted, okay, from data. But what is interesting here is that you have this thing here, number of mosquitoes divided by number of humans, which sounds fine, yes? Because this means that if the number of mosquitoes increases, it's high with respect to the number of humans, then you have a higher value of R0, and possibly you have an epidemic. Therefore, there's a threshold value actually for the number of mosquitoes. You have to have enough mosquitoes in order to generate an epidemic. Yeah? And also, if the number of people increases, the number of human individuals increases, you decrease the R0. Okay? So, that's what this is nice. We can have some criticism about this. Yeah, lots of criticism possible. We are not really looking. So, you know, humans are necessary. So we are here. We are taking that the only infected hosts are the humans. We could have more hosts. Okay, actually, we have worked about that times ago, 10 years ago, with Nat and other people from public health, with a model where you have that the population of mosquitoes could have multiple the virus. It was malaria. For the etiological agent of malaria could go to humans, but could also go to other animals. But the other animals, what is the effect? They don't transmit because malaria is completely co-evolved with humans. So only humans have malaria. So the cycle, but the fact that the mosquito divides the biting between the humans and maybe the chicken or whatever they find there, makes the number of bites for possible infections in humans decrease. Therefore, you have a kind of dilution effect. So that is what people are looking in, usually in a subject called disease ecology, because you have an ecological effect of diversity, creating a kind of service, creating a situation where it's unlikely that you will get malaria infections, or could also be other things. So this is something that is interesting. We have worked with data from the south of the state of São Paulo. It's called Ilha do Araújo, where you actually find the mosquito that transmits malaria, Anopheles. But you don't have cases of malaria. First of all, you don't have so many people there, okay? But, yeah, so other criticism is maybe the humans, the fact that they are bitten and therefore they are kind of nutrients for the mosquitoes, the fact that you have more humans will increase the population of mosquitoes. That could happen. So this depends pretty much of knowledge of the biological interaction between mosquitoes and humans. If the mosquito only bites humans, because if, for instance, here I have the number of mosquitoes divided by the number of humans, and I just told you, oh, okay, if you increase the number of humans, that decreases R0, that's nice. But okay, but it could also have an indirect effect of increasing the number of mosquitoes because you are more humans kind of feeding the, so this is not included here, okay? This is not included. That you can do this, you can do this, but then you have to write the demographics of the mosquitoes, okay? So how is the populational dynamic of the mosquitoes? So it includes a part that's more ecological than epidemiological, okay? So this is, okay. Now, what about the solutions? Yes? Okay, I just will show you the plot of the solutions because they have been done numerically, and the assumptions would be that the population of mosquitoes and the population of humans are constants. Therefore, this B here this B will just provide a constant population by equilibrating the death rate with the birth rate. Okay, and so here, so oh. Well, didn't work, and I spoiled everything. Probably the guy will appear here in some minutes. Spoiled everything. So I will tell you in words. So what you have is something like that. So you can already imagine, let's say, infected humans. Yeah, that's what we are more interested. Yeah. You can already imagine that you will have an endemic equilibrium because I have vital dynamics, and the result in the class about vital dynamics was instead of having the burnout of the epidemic, you have oscillations that settle to endemic state. And that's what happens here, okay? You have initially you have a burst of infections, and then you go on and go to an endemic equilibrium. So you can calculate from the equations the endemic equilibrium here in terms of R0 and other parameters. I won't do this because it will give not very much information, okay? So, and obviously if R0 is big, the equilibrium here has a high number of infected. If the R0 is close to 1, it will be here. And no big emotions here, okay? So, but now, okay, so we have a model, and this is it's not exactly the model that was written at kind of 100 years ago by Ross and McDowell, but it's essentially the same. They made something a little bit different, but so okay. So the result here is that we have an endemic state, and we have this dependence here, which is important. Now, you can also say, okay, yeah, nice, but as it is the case with all vector-borne, mosquito-borne diseases and so on, I don't know the parameters. I cannot parameterize this very easily, okay? Maybe I know the lifespan of the mosquitoes, more or less, but I don't know biting rates and so on and so on. And moreover, I don't know the population of mosquitoes, okay? Neither the infected, neither the susceptibles, neither the total population of mosquitoes, okay? So, and this is the part that is difficult with these models. You get this nice big picture, but when you want to be more realistic with these models, you have a problem, okay? Because you don't know the number of mosquitoes. What can you know? So you can know about the number of mosquitoes. You can put traps in a certain place, that the place they are interested, and see how many mosquitoes I get per week, say. Okay? But this is not the number of mosquitoes, but this should be proportional to the number of mosquitoes, and it's called infestation index. It's the number of mosquitoes per trap during a certain time. Okay? This can be done, but this is rarely done. Okay? Because it's costly also. But we have an example in the city of Santos, here near São Paulo. Okay? It's the biggest port of Brazil. So they have data. They have hired a company that works with mosquito control and so on, and they have put I think 400 or 300 traps in Santos. So it's a lot, and they have data for more than 10 years. That's super special, because you don't know the number of mosquitoes, but you know the trends. You know a lot of the population fluctuation of mosquitoes. Okay, so this is very nice, and in this case, you are interested in Aedes aegypti for dengue dynamics. Okay, not malaria. So you can also do other things like instead of trying to test mosquitoes that you get, you can also make batches of mosquitoes and test the whole batch. And then you have, instead of mosquitoes, you have infected batches, and then you try to extrapolate this for the population of mosquitoes, which is more or less similar to putting traps. So, now, one particular thing which is nice, this is a little bit more mathematical, but I will just mention it, is that you could take into account that the time span and birth rate of the mosquito, and the time span, the life time span of a mosquito is much, 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 much more shorter than the humans. And obviously, the birth rate, the number of mosquitoes that are born by unit time, is much higher. Okay? So then you could say, okay, what is the effect of this? There, you can do this more rigorously, but well, what the effect will be that the mosquito settles to a kind of constant population very quickly. And the human disease dynamic is still going on, but the mosquito settles very quickly to the equilibrium value of mosquitoes. So, and this means that I can go here, my mosquitoes equation, and put this derivative is equal to 0. Okay? I suppose this is equal to 0. Okay? So if I do this, I will have an equation for I can calculate the susceptible population of mosquitoes here in terms of the infected number of humans. And I can calculate the infected number of mosquitoes in terms of the susceptible number of mosquitoes, which you calculated in the previous step. So you can get the equilibrium values, which I would call SM star and I star M. I don't want to do all the algebra because we will get lost in the algebra and lose a lot of time. I just want you to see that this is possible to do. So once then you get this, and then we say, okay, the population of mosquitoes of susceptibles and infected is constant, and I put it here. And this becomes an SIR model without the vectors. I mean, the vectors are constants, but they will just redefine here this beta, okay? If you have the infected susceptible and the infected mosquitoes here, infected mosquitoes here, then if you have this value, you could say this is constant now because the population has already settled to an equilibrium. These two equations are not anymore present. You have an SIR model with redefined betas. But and this is not a problem because anyhow you don't know this guy. And that the beta is always fitted, okay, from data. So you can work with mosquito-borne diseases in situations, with models that do not have the mosquito. Obviously, if you have to be sure that this assumption that the lifespan and so on, this is usually for mosquitoes. Not every vector will fulfill the conditions, and you have to have the full model. But for mosquitoes, it's usually okay to work with an SIR model where the beta, the infections rate, will just look like a redefined beta, which you call it beta, beta bar. It's the new beta. Okay? So this is nice, and it tells you also that although I have a more complete system, this system of with this approximation here is also makes this problem easier. This kind of approximation is called quasi-stationary approximation. Now, maybe you are enthusiastic about this, so let me tell you where I actually took this, okay? I took this from the book of Killing and Rouhani, they have a chapter of vector-borne diseases. I took this from that reference, with slightly modifications of the notation, and they also discuss this thing here. And also there are things that they also discuss this. For instance, if you have more things like zoonosis. Zoonosis is it's a disease that is transmitted by some animal to humans. But you usually use the name zoonosis for diseases that animals can transmit to humans, but humans are not in the main driver of the epidemic in the animals. The epidemic in the animals goes on, and it only spills over to humans. So in order to study this kind of thing, this is not okay. So what would you have to do next, guys? You would have to study the epidemic dynamics and population of the animals, of the hosts, and then consider the possibility of spillover with some ratios and so on. But this is difficult because, animals don't go to hospitals, and there's no surveillance saying, oh, this guy's... So this is, for instance, the case with leishmaniasis. Leishmaniasis is a problem. There are rodents, you're not even sure what are exactly the species of rodents that transmit it. And what you have is just, okay, if you have a lot of rodents, it could be more likely to have something going on. But really studying the epidemics of leishmaniasis with compartmental models and so on, there's no big point because you don't have the data about the animals. And in this case, the data about the animals would be very important. Okay? You also have different situations if the host is like a flea. A flea stays on the host. It doesn't bite, it bites, but it doesn't go away like a mosquito. Okay? It stays there. So then you have to make some modifications here also. Yeah. Yeah, well back here. Yeah, then, so let me just for a general audience. So one way that people are trying to control the mosquito, the Aedes aegypti population is by infecting the mosquitoes with a bacterium called Wolbachia. 60 or 70% of mosquito species in the world have Wolbachia, naturally. It's a symbiont. But it is not the case for Aedes aegypti. So you have to artificially go there and infect it. Okay, what happens when you're infected? It doesn't die, but it doesn't transmit dengue. And the first kind of a vaccine for the mosquito, okay? So what would you do? Well, you have to write a model like this one for vector-borne disease, but then you have also take into account that there are mosquitoes that are vaccinated, literally vaccinated, okay? And then it depends, I don't know the state of art of this over the last 3 or 4 years, but you have a problem, okay, have a principal problem. Why does Aedes aegypti not have Wolbachia naturally? And this kind of question can be only answered with evolutionary theory, okay? Because why? Okay. So we don't know, but it could be that this mosquito had some disadvantage having Wolbachia, which means that it's difficult to maintain the population of Wolbachia in the mosquito population. Okay, so this would be an obstacle. Well, then you have also see if you can transmit Wolbachia from through the eggs of the mosquito. I don't know exactly the situation about this point. And there have been attempts at where this has been best developed is in Australia. So they have large experimental fields and so on and go on. It's not a problem of epidemiology anymore. It's a problem of population dynamics of Aedes aegypti, which is infected by Wolbachia. And so they try to get your population of Aedes aegypti to a lower level. Therefore, you can decrease R0 and not have the. If this could be really made on large scale, that would be fantastic. But I don't think this is so easy, actually. And I think you have to keep putting new collected mosquitoes, infect them in Wolbachia all the time. It's also expensive. Yeah. Yeah. Yeah, newborn. You have the vaccinated class here, okay? And then you say, okay, people, mosquitoes can be born vaccinated or not, or infected or not with Wolbachia. So you have a class of Wolbachia infected, but these Wolbachia infected can then also reproduce and create not a susceptible or Wolbachia free. You can create a Wolbachia directly, a newborn with Wolbachia. I don't know the efficiency of this process, actually. Okay, that was at the very beginning, like 10 years ago, when this emerged. But that was a problem. That you couldn't get. I think this maybe can depend on the precise strain of Wolbachia. So that have also a lot of microbiological effects involved. You know? Yeah, great. So there have been some field work here in Brazil also based on the works of people from Australia. The first time didn't work well and so on. Other ways of controlling mosquitoes is which is used in more in agriculture, but could try to do something like that with Aedes aegypti. Is the has a horrible name, sterile male mosquito. So you radiate your mosquitoes, some part of mosquitoes, you radiate them, and they become sterile. But they will actually have encounters with females, and then this will not produce an offspring. And then you are effectively diminishing the population in this way. So this is used in pest control. Okay? But it depends also if the females have more than one male or not. If they have only one time a male, then the guy is sterile. This female has no offspring. But if polygamy is going on with the mosquitoes, then it's more difficult. Yeah? So, okay. Now, I would like so much to project things here, but I can try to do this again. Yeah. Okay. It's here, not here. Okay, got it. Okay. Well, it's coming. Let's see if it's working. Yeah. See. Okay. So now I have a half an hour about a kind of free discussion about some topics that are subject of present research, and have some that are perspectives of further research. But you want no, okay. Well, I will have to do. Okay, this was you see the endemic equilibrium in the book of Kiliruani. So, okay. First, I have a list, non-exhaustive list of things that I thought a little bit. So, one of the things has to do with the mosquito dynamics and vector-borne diseases, or any kind of vector, not necessarily mosquitoes. So these diseases have geographical ranges, right? So you don't have malaria in Patagonia, for instance, okay? Nor in northern Europe, although you had malaria in Italy until the Second World War, okay? It was eliminated. So there are geographical bounds, and what this is connected to the fact that if you are talking mosquitoes and also some other mites or so on, they do not regulate their temperature, right? So this means that the temperature affects overwhelmingly these populations, okay? So this creates borders for the population of the vector, but also creates borders for the transmission of the vector. So you have a geographical range for your possible mosquitoes, but there is a smaller range for the infection. Why? At the borders, you have probably a situation that is like the temperature is too low. If you cross the border, then you don't have anymore your vector. But in order to have transmission, you need the vector, but the vector has to be able to transmit. Okay? So you can have vectors, but in a certain range of temperatures or maybe humidity, you do not have transmission. Which means that you can have for instance, that was true with cases in northern Argentina of malaria. That's now eliminated, but there were these cases. And the point is, you had mosquitoes also in a certain region. This was in the region of Salta, at the border with Bolivia. But you go a little bit further south, you had it in Tucumán, you had also found mosquitoes, right? But there is something which is called the extrinsic incubation time, which is a mosquito comes here and picks you. Eh? You're infected. The mosquito does not transmit immediately. It takes some time. There's a process in the individual mosquito. After some time, usually some days, it will be infectious. Okay, so it has a kind of latency. And everything on mosquitoes depends on temperature. And also the extrinsic incubation period depends on temperature. Therefore, if the temperature, and how does it depend? High temperatures provide quick extrinsic incubation periods, and low temperatures have longer incubation periods. But if it's so cold that the incubation period would be greater than the lifespan of the mosquito, so it cannot transmit. Although it has been infected, it doesn't transmit. Yeah? So this is an example of one of the areas. Oh, it's not mirroring. Oh no, it's okay. This is one of the areas of research that is the research at the border of occurrences of disease. And this is very important because connect directly to climate change. So this connects also with a lot of things with for instance, of in ecology and biodiversity and so on. So these regions that are borders are interesting to study. And this is one thing. So another thing that is important is what I would call, in general, to take account in models of heterogeneities. What kind of heterogeneities? Well, you know, people are not all the same. So people have more resistance to some disease or not. So when you have the transmission, maybe your susceptibility is not a fixed constant for the population. Okay? There are more susceptible people and less susceptible people. You have a distribution of susceptibilities. And you also have a distribution of possible values of the infectivity of an agent. Okay? So this says that actually in your models, when you have the beta, maybe the beta now is a probability distribution instead of a number. Okay? And this takes you to new models. And there are people that have studied this. There have been a lot of things about this, because it apparently could lead to lower values of the herd immunity threshold. And there had been a very bad dispute actually during COVID about that. Okay, so models with heterogeneities in susceptibility and infectivity, that they showed that the situation would not be as bad as this was believed. But this is before the variants. Okay, with the variants, all of this is irrelevant. But that was the case, and this. And actually, our group studied a lot this paper, because the author is somebody I know not very well, but a researcher from Portugal, and the problem again was, okay, the susceptibilities can be have a distribution now instead of having a fixed value. How is this distribution? How do you measure that? Well, this is difficult. You have to make lots of assumptions about the form of the distribution. Is it what? What is this? So log normal or whatever? But what is the kind of situation you have? So all of these are assumptions. And then you have a lot of fitting parameters for these distributions. And this creates models that are not robust. And you get the results depending on the country and so on you study. But they are not robust. If you make a little bit different assumptions, then everything changes. So this is a problem. But studying heterogeneities is clearly relevant. There are other heterogeneities. Well, spatial heterogeneities. Not everything is the same place. We didn't talk about spatial epidemiology. Lack of time. It's a fascinating subject also. So, but then you have this kind of thing that there are heterogeneities of all kinds in the individuals, in the pathogens, in space. The risk heterogeneity, which we briefly discussed, and all of this forms today an area of research that is being explored. Say how the heterogeneities affect the basic facts. Another thing is, there's a nice paper here from, I think from last year, maybe 24, yeah. That is this paper. What's next? Using infectious disease mathematical modeling to address health disparities. So if you want to wonder a little bit more, get more fuller discussion, I recommend this paper. This second author, Mark Lipzig, is from Harvard. Is one of the most important epidemiologists, modelers in the world. He actually he after we say after COVID, but COVID is still here. That after the worst part of the pandemic, the American CDC, or no, I don't know, it's CDC, maybe it's NIH, created an institute to try to work with predictive epidemics, and predict and prevent epidemics based on modeling. And this Mark Lipzig is actually the director. I don't know what happened when Trump came in with this institute, or if he is still there or not, I don't know. But he was, okay? So, and what he stresses, one thing is, it was something that we learned with COVID, because it was an emergency. Then you had the phone companies, the cell phone companies, giving up their data to people in public health about because they can have they know where you are, okay? Unless you get off your cell phone, they know where we are. They know where the people go on and so on. There's a lot of information, so they know mobility. So why not try to make better models, taking into account mobility at several possible scales. Well, one scale is heterogeneity in a city. For instance, taking into account that there are rush hours and so on, and where are people going from one place to another, and how does this impact the epidemic dynamics? This is just a very first step only. We have here almost nothing. But this is something that is really challenging. And then, in the same paper here, he also talks about also agent-based modeling, using mobility. And so another thing is, we know that epidemics impact differently and can also be driven differently according to socio-economical considerations. So we know, for instance, that diseases that impact much more the poor, usually the poor, okay? Or certain regions where you have heterogeneities with sanitation and so on. So could we try to somehow build models that take into account the socio-economical aspects? This is not easy because, you know, what are the essential data that we use in epidemics? It's time series of number of cases, time series of all those things that go on, and the economical data and the socio-economical data, they just are on other scale. They get every 10 years one point of data. So how could you do something with that? But this is clearly important because this touches upon the social determinants of disease. And there are only very few papers that have just started to look at this. Then on the same kind of thing, I was talking mobility, but we could also just talk behavior in general. And this is also very much impacted by the fact that models with COVID had difficulties because you don't have wild epidemics. You have epidemics where you have interventions, human interventions, stay at home, use mask, vaccinate, and so on. So then you could ask yourself, okay, how the behavior of humans, because humans will take some action, yeah? Because I mean, if you have a disease that can kill you, and I'd rather stay at home, or I just travel to some other place, like Newton, fleeing the plague in London, going to the countryside. So there are behaviors, and but yet very difficult to have data about behaviors. Okay, so there's a lot of things here to do including behavioral things. There's some classic work, but this is very much more mathematical, which is about the people deciding to vaccinate or not. And then you use something that's called game theory. And you couple this with an SIR model and see how the game theory impacts. But it's a very theoretical work, actually. It's beautiful, it's really elegant. But we are talking here much more real behavior. Okay? Well, there's also a lot of things that it's older hype, more than 20 years. Right? It's using network theory, and how does network theory imply something about epidemiological dynamics? So we know the classic works, and if you want a name to Google this down, look for Vespignani, Alessandro Vespignani. He has a book also. It's dynamics on networks or something like that. But it's already 20 years old or even more. So you consider networks, and then you can have different things. But one thing is every individual is a point of your network, and then you have connection between them, saying that it's a contact. And then you consider that maybe the contacts are heterogeneous. The number of contacts that you have is your degree of this person. And then you have a distribution of degrees, because it's not like our models, which everybody can have contact with everybody. No, these people have contacts. And then each point of your network can be in the state of susceptibles, infected, of recovered, or whatever the dynamics of the disease is. And then you run the dynamics on the network with the contact structures. Okay? So this has been made. Okay, there's even already books about it. It's more mathematical. It's not very easy, and so on. But then there are also problems with this, which are not easy. For instance, what's the disease you are considering? So, depending on the disease, it has a certain transmission route, and the transmission route will obviously determine what contacts are going on. So it's a respiratory disease. What is a contact? Are we all in contact? Or just, do you have this kind of effective definition, staying less than 2 meters apart for at least 50 minutes? This is more epidemiologist effective definitions. But you know, with COVID, we discovered that COVID is transmitted by aerosols, not droplets. And the aerosols just stay here. Okay, we live here, and there comes another person here and can get COVID and somebody here had COVID. Could happen. So where's the contact? So respiratory diseases have a problem with contacts. Okay? So it's not so easy. Okay? Then the classic case where this works is sexually transmitted diseases, right? Because the contact is defined. But then they have a problem. Okay, lies. Now give me the network, and I will see run the theory on a real network and so on. Yeah, how do you get the network? So you have to interview people and ask them with whom they had sex. And people lie. People absolutely lie. You can see this even in data, in anonymous data. For instance, we have a data set that's very recently released by the Minister of Health about Mpox. Okay, and the thing is, there are people that say, I'm um, heterosexual, but I make sex only with men, and the persons are men. So these things, people say, but not consistently, and people will not trust the person that is interviewing. Well, what is this guy? Maybe I have a lover or something. Why? Maybe I have a super different life in sexual terms, and people don't say it. Okay? So you have a problem in knowing the kind of network that is going on. I've talked with people that do this sexual transmitted disease and say no networks. Explicit networks, you don't have it. Now, what could you have? You couldn't have the degree distribution. So the degree distribution, it's you just ask people, given a certain range of time, say 1 year, for instance, how many sexual partners they had. And this is the degree of the person. And then you make a histogram for that you collected with many people, and you have a histogram of the number of contacts. Now, this is not the same as having the actual network. You would have something that always starts here with 1. Most people have 1. And then it goes on, it decreases. Right? Now, in the study of networks, one of the things that people do is to distinguish networks that fall very quickly and others that don't. So very quickly is like exponential decay, and not so quick falling is polynomial decay. And polynomial decay is connected to some non-trivial networks. They are complex networks and so on. They have a distribution of degrees that is comes from that. So, and if you do a theoretical work on different kinds of networks, you discover that R0 for instance, for polynomial decay is R0, not exactly this. The invisibility criterion is that all polynomial decays are always invaded, can always be invaded. You have no herd immunity and so on. And but they are also highly heterogeneous. And sometimes it can happen that there is something which is called assortativity. And assortativity means that if I have 10 contacts, it's much more likely that my 10 contacts also have 10 contacts, approximately. And in such a situation, you have the tendency that it is easy for the pathogen to establish itself, but it will stay at this more connected part. It doesn't spread out for the whole population. So this is, has been mentioned in recent work from 22. From this bunch of people, all of them kind of famous people, heavy-tailed sexual contact networks and the monkeypox epidemiology and the global outbreak in 2022. And what is the point is, I don't know if they have the plots here, but they talk a lot. Well, okay, what is the point? So if you want, you can look at this paper. It's in Science. So then, but there's data from UK. UK is very good with data. It's fabulous. They have data. If you don't have data for something, try UK. Okay? So they have made interviews, inquires about the degree distribution of sexual contacts. And that what they discover that there are always some people here, which is commercial sex. But this is populationally not so big, so it's not so relevant. Okay? Then they consider 3 different cases: the men that have sex with men, women that have sex with women, and the network of heterosexual sex. And they discovered that the network of men that have sex with men has a long tail. The polynomial degree fits better. Okay? That means that there are a lot of people that have most of them are still here. Okay? But there's a lot of people here that have like 15, 20. Okay? And in this case, this could be an explanation that the dynamics on such a network is easy to establish the pathogen, but it stays in a core, which is the assortativity thing. So maybe these are assortative networks. We don't know for sure, but that there is this kind of thing that people that go to a lot of clubbing and so on, and then they have several partners per day. But these guys also have several. So this is the kind of assortativity that I was talking about. Maybe this could explain the decay of. I mean, there was a lot of concern. This could kind of spread to the population. Although you rarely die of it, it's very painful, the disease. And then it's just kind of decayed. But it's not that there are no susceptibles. Yeah? We are susceptibles. But decayed, so it's a mystery of why this happened. So there are 2 main things. One is maybe networks of because there's all the mystery. Why is this mainly concentrated in men that have sex with men? Because it can be transmitted to women, from men to women, women to men. But why it stays there 95% in Brazil? That is, this is mystery. Okay? And why did it decay? So the decay can be due to 2 things, 3 things. Vaccination, but in Brazil in 2022 there were not enough vaccines. Okay? Can be the network structure, which gives you naturally that the total size of the epidemic is small. And could also be a change of behavior. And certainly there have been some change of behavior. But actually, change of behavior is not a good news. Because that would say that you would, over the time, require people to not have sex. Which doesn't work. Never worked since many things. Okay, so and finally, so network theory is also important for spatial spread. For instance, networks of airline connections, networks of roads, and you can try to do, for instance, Marcelo had done this kind of work, like for COVID, what would be the most probable point of entry, coming from where, and how it would spread between the main cities of Brazil. So he had done this work, and it came from Italy, because China direct connection is not so important, but Italy is important, or it could come from US, but in Italy it was first, and through Sao Paulo, and that's what happened actually, and then it spreads by the disease travels by plane. Now, my last comment is about this kind of thing, which is called physics-inspired or physics-informed epidemiological modeling. The physics is there for nothing, actually. There's no physics. It means just that you have to follow. So there's a lot of hype about artificial intelligence, yes? But we have to distinguish. Large language machine is a kind of thing that is a language machine. It is based on deep neural networks, but deep machine learning. But machine learning is not only large language machines. It's much more. And there's lots of research, and it's well known for a long time, that large language machines have just found some very efficient tricks to get what you get with ChatGPT and so on. So I'm not talking ChatGPT. I'm talking neural networks, machine learning. So everybody say, no, okay, it's the hype, we want to use machine learning or even large language machine for anything and so on. And they are very problematic things also, so on, so on. But used with care, you can have good things with machine learning. And one of the things is, I have a compartmental model, but I don't have the parameters, but I have data. So I can use machine learning, to learn the parameters, which is akin to fitting, but it's a super efficient fitting. So this is what people are calling now physics informed because of the equations, and just coupled this to neural networks and use the power of has been developed for machine learning algorithms to inform your model. Okay? And this can also be used for very interesting things. One of them is, okay, now this has not been done. This is something that people are talking about. Say you have your model, and you have a certain fit. Maybe could you include in your machine learning algorithm not only these variables I have here, but also variables about socioeconomical things, behavioral things, mobility aspects, and so on. And then you ask yourself, okay, if I include this in my data set, will it improve the model or not? If it improves, means that actually those variables could be important. It doesn't prove that they are, because machine learning has a problem. Interpretability of the results. I think everybody has heard this already, okay? You get the result, many times it's, oh, fine, okay, etc., but you don't know why. So this is a drawback, and this means that machine learning cannot substitute real science, but it can improve things, okay, as a method, okay? So you could have the possibility of taking into account some kind of variables that you don't usually have. Okay, so obviously you need variation in the variable. Say, I don't know, gross domestic product, but obviously for one city or one state or country, it's a fixed number that has no variation. So then you need to have data from several cases and see if that variable, if this actually is having impact on the results of your model. This is nice thing. So, okay, that's it. That's the last class. We have now coffee break and good work in the afternoon. The idea is that obviously tomorrow the order of presentation would be random. There's no, but we can maintain the last one if nobody has anything against it. Okay. Okay. So we start. We started with. No, I can't remember, but you remember the 5 in the same sequence as. Okay. Thank you.